Hello everyone, welcome back to ECE100, class number 10. Last class we talked about series equivalent resistance and voltage division. In this class we're going to talk about parallel equivalent resistance and current division. So these questions we will discuss them from your lab. So we're going to wait until you finish your lab and come to class to answer these questions. So let's get to the next slide. So remember that in series connection, all the elements shares the same current. And for the parallel connection, all the elements connected in parallel will share the same voltage. So that voltage across R1 is same as voltage across R2. And equivalent resistance for the parallel connection is follows this equation over here. R equivalent, it would be 1 over R1 plus 1 over R2, 1 over R3, and all the way to 1 over Rn. All right, so that is equivalent resistance for a parallel connection. So if you can simplify this a little bit. You can use this like that. Just some algebraic simplification over here. So you can use that equation, either one will give you the same answer, okay? So that's the equivalent resistance for a parallel connected resistive network. All right, so we're gonna, if we do the math over here, for these two connections, as you see, over here, first one, we're gonna justify that in the class. The first one should give you R equivalent is 11.4. You can justify that using equations, and you can see that the equivalent resistance of this is smaller than the smaller resistance in the parallel connection. So R equivalent for parallel connection is smaller than the smallest resistance in parallel connection. So you can see that R equivalent is 11.4, which is smaller than the smallest one, which is 20 here. This is always true. And for the next one, you see the huge difference, 101. So your equivalent resistance should be smaller than 1 or very close to 1 because the difference is too high. If you do this one here, your R equivalent would be 0.999 ohm, which again smaller than the smallest one and very close to that one because the difference is really high between them. So current division. So let's see here. You have a so if I do the equivalent resistance over here, right, R equivalent, it would be 1 over R1, 1 over R2 inverse. That's R equivalent here. Then your circuit, this circuit would become like this. That means you can replace your both resistor with R equivalent. So now, if the current here is I, the same current also here, right? So now you can see what is that for this circuit over here, you can now express, this is R equivalent over here. You can express your Vs as I R EQ, right? From this circuit, you can see that Vs is I R EQ. And also, if you look at the current over here, let's say I1 here, and current here is I2. From that circuit, you can also see that your I1, right, using Ohm's law, it would be Vs over R1. And I2 would be Vs over R2, right? So now, come over here, your I1, I know Vs from this equation right here. I can substitute Vs over there, should be I R EQ over R1, and same here I2 would be I R EQ over I2. So you can see that now, excuse me, you can see that now that there's a common equation actually surfacing there. So if the I is same, REQ is same, only changing is R1, R2, right? So if I look at RII for any branch in the parallel connections, that's simply I over R EQ over Ri. So I could be 1, 2, 3, and so on. So this is the common equation, generic equation for current division. All right. So if you look at the kth current to the kth resistor here, so I k would be I, which is total current here, right? And Vs over here would be I R EQ over RK. So we're gonna do this in the class, and also gonna do that in the class. So that's all for the current division. For the current divisions, you are working with the parallel circuit, and parallel circuit, parallel resistors, they share the same voltage, and current division equations has a common format. So just use the equation to find the current in a parallel circuit.